Okay, just while we're setting up, I just wanted to introduce the course. So we have 6 lectures. And in those 6 lectures, what I want to do is give an overview at quite a basic level of the fundamentals of the physics of the atmosphere for basically radiation and cloud physics. But because it's a short course, I've actually changed the syllabus a little bit this year. So what I wanted to do is give the course a little bit of a focus. So rather than just picking out a little bit of cloud physics and a little bit of radiation, I wanted to try and give it a little bit more of a purpose. So what I've done is I've changed the syllabus to present the cloud physics and radiation with the purpose of explaining the basic physics in climate models. So it's more directed towards the understanding of models that are used for climate change and also weather forecasting. Okay, so that when you see, for example, discussion of climate change and global models in the literature, and people talk about the uncertainties of climate modeling, then you'll be able to say, I know a little bit about what they're talking about there. They're talking about the way that the radiative processes of the radiation from the sun interacts with the atmosphere, the radiation from the earth is interacting with the atmosphere, and how, for example, the clouds are represented in those models. So what I'm going to do, first of all, is I have this week, basically I'll be discussing the processes of radiation and clouds in the atmosphere, okay? And then in the second week, I'm going to be talking a little bit about how they're represented in climate and weather forecast models, okay? So hopefully it should just be about right for the 6 lectures, because it's the first year I've tried this new syllabus to give it a little bit more focus on the climate modeling. But hopefully that will motivate the topic a little bit more. But before we start that, I've got a few slides, I should say, just motivating what we're going to talk about in terms of the processes in the atmosphere. So just to start us off, I usually start with this figure here, which I don't know if you've seen a figure like this before. What it's showing is on the x-axis here we have latitude, okay? So we're going from the North Pole down to the South Pole. And then on the y-axis we have 2 lines, and they're telling us about the energy balance in terms of the energy that's arriving to the Earth from the sun and the energy that's leaving the Earth's surface in the form of radiation as well, okay? And the difference between those lines is shaded. And the colors essentially are telling us that in the region around the tropics, we have essentially a net gain of energy. So the top line is the solar curve from the sun, and the bottom line is the infrared. So it's shaded red because it's telling us that we have more energy arriving at those latitudes than is leaving. So we have a net input of energy at the Earth's surface, the Earth atmosphere system. Instead, if we look at the regions near the poles, we have the blue shading, which is telling us the opposite is the case. The loss of the energy from the Earth is greater than the input, okay? So if we have, for example, let's have a look at the tropics. If we have a net gain of energy, why do we think it is? I mean, what would we expect to happen normally? If we have a net input of energy, what would happen to the temperature usually? It would increase, yes. But we know that, okay, temperature changes from year to year, and in fact there is a slow long-term warming trend due to climate change, which we'll talk about in today and tomorrow's lecture. But if we ignore the climate change for the moment, we know that although we have variability from year to year in the tropics, there's not a net increase in temperature. More or less, some years it's slightly warmer, some years cooler, but the temperature, in fact, in the tropics is very stable. So if we have a net gain of radiative energy from the sun, but the temperature is not increasing, what do we think is actually happening then to that energy? It's been transported, exactly. So the energy is being transported. Where is it being transported to? exactly, to the poles. And how is it being transported? Any ideas? Exactly, by oceans and the atmosphere. So by motions in the atmosphere and the oceans. So we know that we have energy imbalances often. We have instability. Let's imagine we want to boil an egg. So we put a pan of water on the stove and we start to heat it. We're heating it from the bottom. We have instability. What happens to the water? It starts to move. We have convection. Okay. And that convection is taking the warm, lighter water upwards and the cooler water is sinking. And that's representing a net transport of energy. So you can imagine in a way that the atmospheric system is a little bit like a boiling pot of water. It's been warmed at the tropics and it's being cooled at the poles. So this is essentially saying what we've just discussed, that because of this imbalance, we're driving circulation. So let's have a look at a schematic of those circulations. So essentially what we have is we have a system where in the net, air which is being warmed in the tropics is rising and it's being transported and it's sinking over the polar regions. It's not quite as simple as a... Am I not switched on? Let's have a look. Mute. Ah, okay, there we go. Sorry, I forgot about that. Okay. I don't know what you want to do with that. Is that okay there? There you go, I've ruined the video. We're filmed anyway, normally always over there, so kind of used to it. It's terrible. All the mistakes are online for like years afterwards. All your colleagues back in Reading University and all the other ones that you knew from before, like watch it and then say, aha, so you made a mistake today. So anyway, this is not quite as simple as like a pot of boiling water, and the reason why is that the Earth is rotating. Okay, and so the rotation essentially causes these circulations to be deflected, known as the Coriolis Effect. And I'm sure you've talked about this already in the overview of dynamics with Fred, for example, in his lectures. So I'm not going to be in these courses talking about the dynamics of the atmosphere. What I want to be talking about and explaining is, first of all, how the radiation is interacting with the atmosphere, okay, and the Earth's surface, in a simple energy balance model of the planetary system. And then I want to talk about these things here on this cartoon, these clouds, okay, because clouds are extremely important because they interact both with the solar radiation and also with the radiation that's emitted from the Earth's surface. And so we're going to learn about how one of the biggest uncertainties in climate modeling is actually the way we represent these things in our models, these clouds, which are important for the energy balance and the dynamics. Okay. So just as an introduction again, this is a plot of the temperature structure of the atmosphere. Okay, so we have height on the y-axis here, going from the surface at the bottom up to 100 kilometers. And on the x-axis, we have the temperature. Okay. And so essentially, we split the atmosphere up into discrete layers according to whether the temperature is falling or increasing in those layers. So the temperature at first decreases with height, and we name this part of the atmosphere the troposphere. And this is normally on the order of 10 to 15 kilometers. Okay. Then we have an increase through the stratosphere and then a decrease through the mesosphere. So nearly all of this course, well, in fact, everything I'm going to be talking about over the next 2 weeks is concentrating on the lowest 10 kilometers of the atmosphere, where the majority of the gases are. The atmosphere is extremely thin here. This is where all of the weather is taking place, all of the clouds and so on. Okay. Now, for those of you that stay on and actually do the fall ESP diploma course from next year, we have a big course in the first term that talks all about the thermodynamics of the atmosphere, that describe the reasons why the temperature's dropping, increasing here, and so on. Okay. So why are we concentrating on the troposphere? It's because this is where all of the weather is taking place, and the vast majority of the humidity is there. Okay.
Sir, can you go back to the slide? Could you give us some glimpse why we have such profile of the temperature?
So, I mean, one of the reasons why the temperature is dropping, the main reason here, is simply due to the changing pressure of height. Okay, so whereas we have an increase here because of the gases that are present that absorb the radiation. So when we start to talk about the different gases in the radiation part of the course and what they absorb, and you'll see, for example, ozone present here interacts with the solar radiation, and so the warming of that interaction causes basically a warming here.
In the first 10 kilometers, it looks like a linear, right?
Yes, it's approximately linear. So if you have a dry atmosphere, then this drops by 6.5 Kelvin per kilometer in altitude. Okay, and in a moist atmosphere, then it's actually slightly slower, this drop-off, and that's due to the latent heating due to condensation. Okay. For the moment, just keep this picture in mind of the fact that you have a cooling in height. Okay. So this gives a little bit of a zoom in of that layer that you were just talking about, the fact that we have this drop with temperature of height as the pressure is decreasing with height. But it also shows the differences between the tropics, mid-latitudes, and the poles. So obviously the poles are considerably colder at the surface, okay? And that inflection point at the top of that layer occurs at a lower altitude than it does in the tropics. And this is due to the role of deep convection, these thunderstorms in the tropics that reach a deeper layer due to the stronger warming. So they're able to reach a higher level before we reach this inflection point. Okay. So as I was mentioning, in the stratosphere and the troposphere, we find a large mixture of gases. I'm speaking too quickly, yeah? Sorry, good idea to stop me if it's too fast. So in the atmosphere, we have a mixture of gases which are divided between those which are found in large quantities, okay, and those which we term minor constituents, which are basically, we can almost say, like trace gases, are found in very small concentrations, okay. So the major constituents we can see listed here. So essentially 78% of the atmosphere consists of nitrogen. We have 21% of oxygen. Then we have argon. And then we have listed now we're into the smaller volumes. So for example, carbon dioxide, ppmv. Does anybody know what that stands for? pp? See, exactly, parts per million volume, okay? So we can see these are very small concentrations. We have 380 parts per million, okay? So we're down to fractions of a percent of carbon dioxide. So we're always talking about carbon dioxide for climate and global warming. Carbon dioxide increases in the atmosphere. And yet we have to remember that as a percentage of the atmosphere, it's just a tiny, tiny fraction of a percent. And yet changes in the concentration of this can have a huge impact on the temperature of the surface of the Earth. So all of these gases, to a good degree, you can see, well, I ask a question here, are they well mixed? What that means is if we measure them in one location here at Trieste, and then we go to perhaps somewhere, I don't know, South America, to Chile, and we make a measurement, do we record the same value, or do we record a value that's twice as large or 10 times lower? So something that's well mixed is something that means, you can imagine, it's mixed up everywhere, so no matter where you go on the globe, more or less, within a small degree of variation, you'll measure the same value. So the answers, I mean, we can see we've given the fractions here, and to a good degree, most of these are well mixed. But there's one that in particular stands out. Well, in fact, there are two which are not so well mixed. Okay. So one of them, it's very clear, because in the table we can see water vapor is variable. Okay, so I'm going to talk about that next. So water vapor is not well mixed. It changes a lot from location to location. Okay? And the other one, of course, we can see here is ozone, okay, which also is highly variable. And that depends, well, what do you think it depends on? It depends on the reaction times of ozone with other chemical species in the atmosphere. So the expert in our group on this atmospheric chemistry, and for example, the chemistry that affects ozone is Fabienne Solomon. Okay. I'm just highlighting ozone because it's important for the temperature in the stratosphere. Okay. So most of these gases, they're to a good degree well mixed. It doesn't mean that they're exactly the same. If you're, for example, close to a location with a lot of industry, with a lot of CO2 emission due to coal burning and so on, then you will very slightly have a higher concentration. It will vary by small amounts, but we're not talking about twice as much. Whereas, for example, if you have like sulfate aerosols, pollution that's emitted from cars, for example, those have a very short lifetime because they can be washed out by rain and so on. And so aerosols maybe stay in the atmosphere for just on average 1 week or so, 1 or 2 weeks. And so aerosol concentrations vary a lot from location to location, okay, such as soot and sea salt. And so we'll see, in fact, that that's quite important for cloud physics, because aerosols in the atmosphere, whether they're natural, like sea salt from the ocean, or whether they're artificial, such as soot particles from combustion, they have very short lifetimes, but they have a big role in the formation of clouds, which is actually important for cloud properties from location to location.
Would also factors like, say, temperature, because okay, what I know from the back of my mind is maybe the motion or speeds of the speed at which gases do move is affected by the temperature. So I would expect maybe.
Well, the advection of, for example, pollution in the atmosphere is with the mean flow, okay? But if you have large particles, they will settle by gravitation as well. So it's actually the motions that determine the mixing. For the temperature, some of the chemical reactions are temperature sensitive. So I don't know if you're referring to that. But the actual mixing and advection, so when we say about the carrying of pollution or particles in the atmosphere, is by just the advection process. So it's moving with the wind, like clouds as well. Small cloud droplets have a very slow fall speed, and so to a good approximation, we can just assume that they're moved with the mean flow. So when it's a windy day, you see the clouds are advected along with the mean wind. So the climate is varying from location to location due to the factor we were talking about at the beginning, which is the energy input. So when we get to the radiation slides soon, then you'll start to understand that. So don't worry about should we say, the climate differences for the moment. This is just an overview to kind of introduce the different, should we say, aspects of the climate. But then we'll talk more about the physics in a moment. So I can see you're very keen and you're asking me the questions before we get to the section. So we'll get more clearer when we start to talk about the radiation interaction with the atmosphere. Before we do that, I want to just show you here the way that the water vapor varies as well in the atmosphere. So we said that water vapor it's actually fundamental for the energy balance as well, because although for greenhouse should we say, global warming, you know, the greenhouse effect. We always talk about CO2. In fact, the most important greenhouse gas that increases the surface temperature is water vapor. Okay. And water vapor is highly dependent on your location. So here again we have a plot of the water vapor distribution. And we are going with the solid line. We're showing you the water vapor in the tropics, okay, from 10 south to 10 north. The dotted line is from 40 to 50 north, and then we have the long dashed line, which is from 70 to 84 north, so near the North Pole. And so what characteristics do we see? First of all, what happens to the water vapor as we go up through the atmosphere? It's decreasing, yes? And what happens if we go from the tropics towards the poles? It's also decreasing, okay? So what do you think is the parameter that's determining the water vapor concentrations? This should remind you of...
The amount of radiation reaching a certain area.
Well, it's actually, well, indirectly it's the radiation, but the direct parameter is the temperature. Because if you remember, the temperature, of course, is decreasing towards the poles, but it's also decreasing with height. Okay. Now, the relationship is highly non-linear. Okay, so there's not a linear relationship between temperature and the total amount of water vapor that the atmosphere can hold. It's actually a strongly non-linear temperature relationship. So as the temperature is increasing, okay, the saturation amount of water vapor that in the atmosphere is increasing strongly non-linearly. And again, I'm not going to go into the details of the thermodynamics because that's a long, detailed course. So I just want to give you an overview. But the warmer it is, okay, the greater this limit is of saturation. Okay. In fact, I might actually just draw a diagram to explain that in a little bit more detail. Yes, I can see you're all very enthusiastic. Let's imagine a box, okay? And in the box, we have liquid water, and above that space, we have, at the start, we have a vacuum, okay? Now, on the edges of this liquid, okay, we have molecules at the surface of H2O, and they have basically intermolecular attraction with other molecules. Okay, so we have, because we have hydrogen basically inside water vapor, H2O, then you have attraction, okay, between the molecules. Now, within that water body, there's variation in the kinetic agitation of these molecules. The warmer it is, the more kinetic energy you have, the more vibration. And so some of these molecules will have enough energy to overcome the bonding, the intermolecular bonding, and they will escape from the surface into the space above. What's that process known as normally? Evaporation, exactly. So this is the process of evaporation. Okay. So let's imagine, we started off with a vacuum, but we have some of these molecules that break free. Okay. So this increases the water vapor, the amount of water in the vapor state in the area above, yes? Okay. So if we have a measure of water vapor, here we actually had on the previous plot the specific humidity. It could be also measured just by the partial pressure, the pressure of the water vapor gas. What will happen from evaporation? Will the pressure of the water vapor increase or decrease? Increases, exactly right. So whatever measure we use, it could be specific humidity, or let's just say the partial pressure, which I'm going to denote by E, will increase. Okay. Now, some of these molecules flying around randomly, some of those will crash into the surface, and then the bonding will hold them there. So they'll actually impinge upon the surface, and they'll become stuck, and they'll essentially become caught up by the intermediate bonding and be trapped in the water surface. So they then go back into the state of liquid water. What is that process called? Condensation. Okay. So we have a condensation process and an evaporation process. Now, question 1, what parameter does the evaporation rate depend on? Temperature, exactly. So we just said the higher the temperature, the more basically kinetic agitation of the molecules we have, so the more likely they are to be able to overcome the intermolecular bonding and break free. The higher the temperature, the greater the evaporation rate. Okay. Now, if we increase the amount of water vapor molecules here, okay, for a given number of water vapor molecules, what does the condensation rate actually depend on? What parameter does the condensation rate depend on? Vapor pressure. Very good. So E. The more molecules we have here, the more likely we have to have collisions, yeah? The more cars we put on a motorway, the more accidents we're going to have. Okay. Now, let's imagine a situation where we have an equilibrium. At the beginning, if we have a vacuum, there's no condensation, it's 0, because the vapor pressure is 0. So we only have evaporation. So for a given temperature, we wait, and this is increasing and increasing until eventually the condensation rate will increase and will exactly match the evaporation. Yes? Now, when we have that equilibrium between condensation and evaporation, we say that the air here, or this space above the water, is saturated. Okay. So the air here is said to be saturated, and that means that we have evaporation rates matching condensation. Okay. So in terms of relative humidity, we say the relative humidity is 100%. Okay. That's relative to the saturation amount. So what does the saturation, so we can call it, if we are a saturated state, then we say the vapor pressure is equal to the saturation vapor pressure. I can write it ESAT. What is ESAT a function of? Temperature. I heard someone say temperature. Exactly, because the evaporation rate depends on temperature, and so that increases the vapor pressure. The condensation depends on the vapor pressure, but then, so indirectly, that depends on the temperature. Okay. So the higher the temperature, the higher the saturation vapor pressure. Okay. So what happens if we perturb the system? So we're exactly at saturation, and then I add more molecules, okay, of water vapor. So I just throw some more into the atmosphere. Then this air is said to be supersaturated, okay, because the vapor pressure is greater than ES, okay. Now, in theory, there's no reason why we can't have a higher pressure, vapor pressure, than the saturation vapor pressure. And in fact, when we start to think about ice, that actually often happens, okay? But for just temperatures that exceed 0 degrees, what happens is all of the excess of the vapor pressure above the saturation level immediately condenses, but not necessarily onto a liquid surface, but into droplets in the atmosphere, cloud droplets. So as soon as E exceeds ES, because here we had a very simple picture of a bowl of water with a space above. But what actually happens in the atmosphere is rather than a bowl of water, we have condensation rapidly onto cloud droplets of liquid water. Okay. It's a rather poor diagram because we have large molecules, and of course the liquid droplets in comparison would be this size, much, much, much larger, of course, compared to molecules. So without going into the mathematics, that explains why temperature, okay, determines the amounts of saturation above which all of the excess water vapor condenses rapidly into cloud droplets. Okay. So if we measure water vapor, it's a strong function of temperature because, for example, here in the poles, it can't go much higher because we reach the saturation limit and all of the excess is condensed into liquid droplets, which then maybe form rain droplets and fall out of the atmosphere. So the saturation vapor pressure, which is a function of temperature, represents a natural limit to how much water vapor we can hold in the atmosphere. We increase the temperature, we can hold more water vapor. And in fact, for global warming, that's going to turn out to be important because if by changing carbon dioxide we warm the atmosphere then can hold more water vapor before it forms clouds, and the water vapor is also a greenhouse gas, which leads to more warming. Okay, so you get an amplification of your initial perturbation, which are called climate feedbacks. So I'm already giving a few feeders towards the climate modeling. Okay. And this is why global climate modeling is not as simple as it first seems, because the things that you perturb, like carbon dioxide, are only one factor in a very complicated system, and then there are all sorts of other things that can change to reduce or amplify the effect. And those give you the uncertainty. So we're going to talk about a few of those examples.
To a small scale, if at all I was having a given volume of water, the rate of evaporation is also dependent upon the concentration of the humidity. How much vapor you already have above?
No, no. Because what you're mixing up here is you're thinking about the rate of evaporation in terms of the net evaporation. What you're thinking of is, again, if we have a water vapor body, if you have a lot of water vapor molecules above, in other words, we have very humid conditions, you're saying it reduces the rate of evaporation. What it changes is the net difference between the condensation rate and the evaporation rate. Let's have a think for a moment. If we want to dry our clothes, okay, when do they dry the best? When we have a relative humidity of 20% or a relative humidity of 100%? 20%. Why is that? Because when we have a low relative humidity, okay, we're subsaturated, the evaporation rate greatly increases, is much greater than the condensation rate. So we have a net loss of humidity from the clothes. But all the time, they're also gaining water, the clothes, from the atmosphere, because water vapor molecules are bumping into the clothes and being absorbed. But there's a net flux because there's more leaving than actually being gained. If it was 100% relative humidity, a really humid day, okay, then it doesn't matter how long you leave those clothes, then they will never dry, okay. And after a couple of days, they'll start to smell really bad. But normally, we never usually have 100% relative humidity. It can be very, if you go to somewhere like the south coast of Ghana, then you can often have 85, 90%, okay. But it's still lower than 100%, unless you're inside a cloud. You know, normally when you have 100% relative humidity is when you have conditions like here in winter. Sometimes you have a low-level cloud, which is called fog. In foggy conditions, your clothes will never dry. Let's make the question slightly more complicated. Okay. What day dries your clothes best? A still day or a windy day? Windy day. Why? Let's see if somebody else wants to have a go who hasn't spoken yet, actually. Not Wednesday or Sunday, no, a still day or a windy day. Maybe Wednesdays are particularly good for drying clothes. Not a sunny day, a windy day or a still day with no wind. Anybody want to have a go? Go on then, have a go.
Okay, seeing there is a wind, okay, the water molecules on the clothes can be, okay, there is wind, then in the atmosphere there are water molecules, and then the temperature, okay, might affect
Okay, time up, ding ding. Do you want to have a go? But how? You're on the right lines, but how is it? Let's think of the situation first of all of the day with no wind, okay? And let's say we start with a relative humidity. We have a relative humidity of 80%, okay? And I have my washing line and I'm hanging out my t-shirt to dry, okay? Now we have no wind at all, and we have conditions of 80% relative humidity. Now I leave the t-shirt there, and I go away, and I come back in an hour's time. What happens to the relative humidity near the t-shirt? Is it still the same, or does it go down, or does it go up? You think it goes down?
Because, okay, there is a wind and the air molecules will combine and then they will
Well, let's just, let's not run ahead. Let's answer the question. What happens to the relative humidity here? Does it go down, stay the same, or go up? Who thinks it goes down? Down. Who thinks it stays the same? Up. And who thinks it goes up? It goes up. Why does it go up? Exactly. Think about this like the water body again. We have a saturated t-shirt, okay, and the relative humidity is 80%, so it's subsaturated, below the saturation level. So the evaporation rate exceeds the condensation rate, yeah? It's just like the water body. We have more loss, I think. So the shirt is getting drier and the air is getting moister. But as the air gets moister, what happens to the net? That's the important thing, the net evaporation rate. The difference between the evaporation and the condensation. What happens to the net evaporation? Does it go down, stay the same, or go up? It goes down, because the relative humidity is increasing, and therefore, as the relative humidity or the vapor pressure increases, the condensation rate gets larger, and the evaporation rate is just a function of temperature. It stays the same. And so the difference between the two, okay, is getting smaller as we tend towards saturated conditions where we have an equilibrium. Now let's let the wind blow. So now we have a net wind. What is the function of the wind? What is it doing? It's very good. It's taken that 90% relative humidity air, it's moving it away, and it's bringing in nice new supply of 80% relative humidity air. Okay. So it's keeping the relative humidity the same, and it's transporting the moisture away from the vicinity of the shirt. Okay. So the net flux remains the same, you see. So just a simple process of drying clothes already tells us a lot about the way, understanding the way the atmosphere works. So this idea of like when it's more humid, the evaporation rate goes down, what you have to think of it's the net, the difference between the evaporation process, which is a function of which parameter? Temperature and temperature only. Okay? And then the condensation rate, which is a function of the vapor pressure, how much vapor we have in the atmosphere. The more vapor we have, the higher the rate of condensation. Okay, good. So now you understand one of the fundamental concepts of how the atmosphere is working. So already the next step to cloud microphysics will be really simple in the lecture later in the week. Okay. So carbon dioxide, I thought I would mention that. As we said, it's well mixed, but it is increasing. So when I talk next week about climate change and climate models, this is the picture you have to bear in mind. So it's like years along the x-axis, and the top plot is the one I want you to concentrate on today, and that's just showing the variation interannually in the carbon dioxide and then the long-term trend. Okay. What's causing the wiggles each year in the carbon dioxide? It's the seasons, yeah. So when we have growth of vegetation, we use up carbon dioxide, okay? And then in the winter, but which winter? Why is it we have, because you think to yourself, well, when it's summer in the northern hemisphere, it's winter in the southern hemisphere, so why does it not balance out? Because we have more land in the northern hemisphere. So it's driven by the seasons in the northern hemisphere. Okay. And so the second part, this is just an introduction, of course, because we're going to talk more details about some of the physics, as we're going to talk about clouds. And this is just an image of the global cloud cover. Okay, this is just a snapshot, and it's taken from satellite, and it's looking at the outgoing long-wave radiation. So it's not a direct measurement like in the, should we say, the visible spectrum, what we see with our eyes, and I'm going to talk about the magnetic spectrum next. It's in the infrared. So what it's actually looking at is telling us about the temperature of either the ground or the atmosphere underneath it. Okay, there's a false color here for the lands and so on. But essentially, these white clouds are very cold clouds, okay, and the grey clouds are very warm clouds. The colouring is telling us the temperature of the cloud that's being measured. Okay. So, if we know the white clouds are cold and the grey clouds are warmer, relatively, which are the low clouds and which are the high clouds? The grey ones here, are these low or high, do you think? Low. Because we can assume, to a good approximation, they have the same temperature as the surrounding air, and we remember that the temperature is falling with height. Okay. So these clouds here have a similar temperature, in fact, to the surface. They're quite warm, and therefore they're coloured grey. These are low clouds. We know that they're low. These clouds here are white, so we know that they're high. They could actually be high and low, very deep, because all we're looking at is the temperature of the cloud top. Okay. But you can see from this that clouds are not a rare occurrence, in fact. Clouds are very common. And in fact, the net mean coverage of clouds, do you know what the mean coverage of clouds is in the atmosphere as a percentage? How much of the globe on average is covered by clouds? Any given day? It's around 65%. Okay, unless you live in England, then it's a little bit higher. But essentially, it's around 65%. But of course, it varies, as I indicated, from place to place. So in the Sahara region, for example, you have a very low mean cloud cover. And these are important because they interact with radiation, and they also are extremely important for the hydrological cycle. And the hydrological cycle means the cycle of water in the atmosphere. Because we said already, as soon as we reach 100% relative humidity, and we keep increasing the water vapor, all of the excess is condensed into cloud droplets, which may then form rain. Not always. One of the big questions, which we're going to try and answer in this course quickly and briefly, is in the 1800s, one of the big unknowns in meteorology is why clouds don't rain. Seems a little bit of a strange question, but if you think about it, it's very common. I bet if I were to open these blinds now and we have a look outside, today's a very nice day, but probably in the afternoon there'll start to be fair weather kind of cumulus. If you remember the weekend, Saturday and Sunday, Saturday was very overcast, but it didn't rain. And so one of the big questions was, why is it that some clouds rain and others don't? And in fact, the majority of the cases when we have clouds, they don't rain. So we're going to try and answer that question as well, trying to understand.
Isn't 65% too much?
Too much? Well, it depends if you work in, should we say, tourism, or whether you're working in rain-fed agriculture, no? If you're a farmer based in, for example, the highlands of Ethiopia, then normally seeing clouds at a certain time of the year is pretty good news, no? On the other hand, if you want tourists to come to your location in Croatia, then you want the clouds to stay away, no? To keep them. But anyway, the percentage of cloud varies a lot, as I said, from location to location. And it also has an annual cycle, as we know, changes with the seasons. So you'll see, particularly here in Trieste, for example, compared to the UK, there's a much stronger annual cycle of the cloud, depending on the large-scale circulation. We have very sunny summers here and wet winters. In the UK, we tend to have the same proportion of rain and cloud the whole year round. There's much less seasonality. So I'm being a little bit flippant there with my answer, but it's a good point to bring up. There is a lot of variability in the cloud cover. So this is actually a cartoon of the atmosphere's radiative processes, again as an introduction. And what I want to emphasize here is the role of clouds in particular of changing the radiation budget. Okay. So the atmosphere Earth system, okay, what we want to talk about in starting of this lecture and tomorrow is the role of the way that radiation interacts with that atmosphere. So the atmosphere itself can absorb radiation that's emitted from the Earth's surface. It can absorb a small amount of the solar radiation, but clouds in particular have a strong role in regulating the Earth's radiation budget. Okay. So what we're going to do in the radiation lecture is we're going to make a very simple energy balance model of the Earth atmosphere solar system. Okay, so the sun and the Earth with the atmosphere. And the atmosphere, as I said, is important. If we were to take the atmosphere away, we take a giant vacuum cleaner and we take away all of the gases, so the Earth is left just as a ball of rock. Okay. Do you know what the mean temperature would be? At the moment, we have a mean temperature on the order of around 15 degrees C. If we take the atmosphere away and we just leave a ball of rock in the same location, do you think it would be colder or warmer without the atmosphere? Colder. And it's a lot colder, in fact. The difference of the atmosphere is on the order of 30 degrees or so. So if we take away the atmosphere, we would actually have a mean temperature at this location and distance from the sun of around -18. Okay, so quite a lot more chilly. So we're going to make a simple energy balance model to try and derive this difference in the radiation course to understand how the atmosphere warms the surface. Okay.
Okay, we've talked about the low and the high clouds. Are there particular clouds responsible for the absorption of radiation?
Well, both the low and the high clouds absorb radiation from the Earth's surface. So we will talk about this. Because they essentially are very efficient at absorbing the wavelengths that the Earth emits. Okay. The exact properties, particularly for the scattering of solar radiation, depend more heavily on the height. And the reason why do you think cloud properties can change for the scattering very much on the height? What do you think changes in what a cloud is made up of if it's very low near the surface? Remember, the temperature near the surface is in the tropics maybe on the order of 20, 25. So if we have a low cloud that's within a kilometer of the surface, what do you think the cloud particles are made up of? Which state is the water in? It's not in the vapor state, we know. Is it liquid or ice? Liquid. The high clouds, can you remember what that temperature graph was going all the way down to around 190 Kelvin at the tropopause? The tropopause, remember, was the difference between the troposphere and the stratosphere. So that division on that graph was the tropopause. That's at around 190 Kelvin. Okay, so in degrees, we're talking on the order of like -80. Okay, so -80 will be ice. So ice crystals will have very different radiative properties than liquid water droplets for the scattering of light, for example. But both of them are very efficient at absorbing infrared radiation. So the properties do change. And we won't be going into the details because I don't have time in particular to talk about the ice microphysics because it's a very complicated subject. You could talk 30 lectures just on cloud microphysics. So we're only going to be going into the overview of the warm rain processes of liquid water droplets and the formation of rain droplets. But you're right. And these are the kind of complications when you get to this fine detail about the ice crystal structure because they can be very different in shapes and so on. It's very difficult to put into a climate model to a good degree of accuracy. Okay. So what I'm mainly going to be talking about, as I said, is radiative and cloud processes, which are important both for short-range predictions with atmospheric models for weather forecasts or longer range predictions for climate models. But this is just to show you that the climate system obviously is a lot more complicated, and there are a whole load of processes that we can't talk about in detail, but I wanted to remind you that they're important to include if we have, for example, a climate model. So we've already talked a little bit about the atmospheric constituents of the different gases, and we're going to talk about how these interact with radiation. Okay, but these are embedded into a much larger climate system where, for example, we have interactions. Let's take an example here with sea ice. Okay, so sea ice can change according to the seasons. Obviously, at the North Pole in the winter, you have a greater extent of sea ice. In the summer, it melts and retracts. Okay, and the sea ice, for example, will be important for determining the amount of solar radiation that's absorbed. Because if you have open ocean or you have ocean covered in sea ice, which of those two do you think absorbs the most sunlight from the sun, the most radiation from the sun? Open ocean, yes. Because the open ocean has a much lower, what we call, we'll introduce the term albedo. The albedo is essentially the proportion of the light that's reflected back. So we know from experience, if we're on a snowy or icy surface, it's very bright. We normally need sunglasses. There's a lot of light that's reflected back up, whereas an ocean is much darker. If you look at an acute angle, you have glint, but usually if you look directly down at the ocean, it's very dark because it's absorbing a lot of the sunlight that's actually arriving at the ocean surface. So if we have a lot of sea ice, we have a lot less absorption of solar radiation. So for a weather forecast model, so we want to make a forecast for the weather for the next 5 days, would we want to have in our weather forecast model a subcomponent that models the changing of sea ice, do you think? Is that important? That models the way that sea ice changes over the next 5 days? No. Why not?
Because it's something depending on the season, something depending on long time.
Exactly. So it's a very slowly evolving component. So in a weather forecast model for the next 5 days, the changes are going to be tiny, so we can ignore them. We still might want to describe how much sea ice we have, but we can just say, measure it now and just assume it stays the same. So we don't waste computer time running a sea ice model that changes the ice by a fraction of a percent. Instead, for a climate model where we want to run for the next 50 years, of course, then the changing of the sea ice from season to season, and also from year to year, maybe if it's getting warmer, then the sea ice is slowly reducing. And you can see the less sea ice, the more solar absorption, the more warming, leading to less sea ice. What do we have? We have another feedback. Increase in the carbon dioxide will warm the atmosphere, but it may be amplified by the reductions in the sea ice. So for a climate model, we would want to have a model that actually, rather than just fixing the sea ice, can tell us how, for a given sea temperature, the sea ice will be growing in depth and also expansion. So that's just one example. I don't want to go into all of the details. One of the things I'm working on with one of my postdocs at the moment, for example, is forestation changes, again, which change albedo, that change the roughness of the surface for the winds and so on. And so we're looking at a dynamical forest component for one of these climate models to try and improve the representation of changes in forest cover over time due to man-made deforestation. But that's just to point out that some of these processes are fast timescales and some of them are longer timescales. And so the fast timescale processes, such as clouds, which evolve on the order of minutes to hours, are important both for weather forecasting and also for climate modeling, because over long timescales, the properties of those clouds could change. Okay. Okay. So we have half an hour left. Yeah, that's correct. So weather forecast models, in fact, they have components that actually model how much of the surface is covered by snow. And that's particularly important if you want to forecast the 2-meter temperature, which is an important parameter for weather forecast. People want to know, we live on the surface, so we want to know what the surface temperature is going to be, what the precipitation is going to be, the level of cloudiness. And so you're right that the snow component is something that's actually dynamically forecast in weather forecast models. Before I actually came to work here, in fact, I worked for 7 years in an operational weather forecast center. And then before that, I was working 3 years in a climate center in Germany. So I've been quite lucky because I've been able to work with the two systems to see the differences, the long timescales and the short timescales. So you're right that the snow is an important component. So we have half an hour now. I'm going to start talking about radiation. Do we have any other questions before I move on from the introduction? Or is that fairly clear so far? Okay. Am I still speaking too quickly? Yes. Okay, I will try and slow down. You do need to interrupt me if I go too quickly. When I start to get excited, I always speed up. No? So, okay, so to motivate you, we have a picture of the sun. Okay, the sun. I'm sure you'll recognize it with all its turbulent activity. As you've probably already realized from the introduction, the sun is the ultimate source of pretty much all of our energy. Okay. So what we're going to talk about now is the way that the energy that's arriving from the sun is interacting with the atmosphere and the surface of the Earth, and how that's changing over longer timescales as well. Okay. So I'm sure this is familiar to most of you, so bear with me if this is a repetition, but it's important to have some of these, basic concepts clear. So when we're talking about different parts of the spectrum, okay, we have to remember, keep in your mind that we are talking just about a subsection of the total electromagnetic spectrum. That's basically describing the complete range of frequencies and wavelengths of electromagnetic radiation. Okay. So for reasons that will become clear in a moment, when we're talking about the Earth atmosphere system, we often refer to infrared radiation or solar radiation. So on the complete electromagnetic spectrum, we're really talking about this area here, okay, in the far thermal infrared. And then we're talking about this area here in the solar radiation part, of which the visible component, to which our eyes are sensitive, is only a very small subsection of the solar bands. Okay, so we're really talking about this subsection of the electromagnetic spectrum. Okay, and so when we talk about the electromagnetic spectrum of an object, we're talking about the, as I say here, the characteristic distribution of the radiation that's maybe emitted from that object as a function of the wavelength or frequency. Okay? So what we have in mind is a very simple, I've got this cartoon here, this schematic of the Sun-Earth system. So we have the Earth orbiting around the Sun at a certain distance, RD, okay? And we have an Earth of radius RE and a Sun of radius RS. So this is our very simple picture of the Earth atmosphere system. And so the first thing we're going to assume is that the Sun is emitting energy as a black body. So what does that mean? The Blackbody radiation, is that familiar to all of you as a concept? I don't know how the different backgrounds. I'm hoping that some of these physics concepts will have already been covered in some of your previous scientific lives. So a black body is an object that absorbs all electromagnetic radiation that falls on it, okay? No radiation can pass through it, okay, and none is reflected, okay? So we can say it's a perfect absorber across all of the wavelengths and frequencies. And it's also a perfect emitter of radiation at the same time, okay? So if we have an equilibrium, an object in equilibrium with its environment, I say, it has a spectrum that depends only on the temperature of that body, okay? And the temperature is related directly to the wavelength of the light that it emits, okay?
Which equilibrium does it have? Mechanics, equilibrium, thermodynamics?
So if we have a radiative equilibrium, so we're talking about a situation where we have a body, okay, that's in an environment where it's essentially in an equilibrium where the radiation that's emitted is exactly equal in a black body to all of that that's absorbed, okay? And the wavelengths will depend on temperature. So we'll see the equation that describes that functionality in just a moment. That will become clear as we go through the slides, I hope. But before we go on to that, the other thing I need to introduce is the concept of irradiance and radiant emittance. So irradiance and radiant emittance, okay, are terms that describe the power of the electromagnetic radiation that arrives or leaves a flat plate per unit area, and we integrate over the hemisphere. So if we have a flat plate that's 1 meter square, okay, we're integrating over a hemisphere above that flat plate, okay. So we're essentially measuring the amount of radiation that's coming from any angle or direction to this flat plate, okay. So normally we refer to this as radiant emittance if the radiation is leaving the plate over the hemisphere, or irradiance is the radiation that's arriving to the plate over the hemisphere. Okay. So the total energy per unit time is known as the radiant flux, and it has units of joules per second or watts. So as we're measuring for a unit area, so we had a plate here of 1 square meter, for example, then the units for essentially of radiance emittance will be watts per meter squared or joules per second per meter squared. So there's nothing in this definition that tells us the direction from which the radiation is coming. Okay? So Planck's function is the law that describes the spectral radiance of electromagnetic radiation at all wavelengths from a black body at a certain temperature. So we're not going to go into the derivation. But the main thing to see from this is that the amount of radiation emitted from an object at a given wavelength, lambda, okay, is essentially a function of the temperature of that body, okay? And we have a strong function of the wavelength itself. So h here we have is the Planck's constant, and k is the Boltzmann's constant. So this is the emitted power per unit area of an emitting surface per unit, and I haven't described the solid angle, but essentially the solid angle is, if we're looking out from a point, it is the unit area that an object in space subtends at the point of the viewer. So if I'm looking, for example, at that box on the wall, it has a certain solid angle, okay? Now, if I move closer to the box, the proportion that it occupies of my hemisphere is larger, so it has a larger solid angle. So the solid angle is just telling me that the amount of my hemisphere that's covered by an object in space. Okay. So the emitted power per unit surface area, per unit solid angle, and per wavelength. Okay. So at room temperature, black bodies emit mostly infrared light, okay? But as the temperature increases, then we start to emit lights at basically a changing frequency. So as we go to basically higher and higher temperatures, we go from infrared through the visible into the basically shortwave after we leave the white. So then we go along right through to the ultraviolet. So I've got a diagram here that tries to illustrate that. So what I've done here is I've just coded up a simple little toy program that plots on the x-axis the wavelength in microns, okay, and then on the y-axis the Planck function. So what this is telling us is that, and it's for 3 different temperatures, okay, of a body. So we have a body at 300 Kelvin, 250 Kelvin, and 200 Kelvin, okay. So what this is saying is, if we go back to the Planck function, that we fix a temperature T is saying, how does the radiation emitted change as a function of wavelength, okay, for a given temperature? And I've got 3 curves because I've changed the temperature that I've plugged into this equation. So it's telling us how much, as a function of temperature, how much radiation is emitted, okay, at each wavelength by a black body. So this is the longer wavelengths, this is the shorter wavelengths. So what we can see first of all is we have a curve with a peak value, okay. What happens to that peak value as the temperature of the body is increasing? It's shifted. So we see that the warmer the temperature, the shorter the wavelength of the peak, yeah? Okay. So if we have a cooler temperature, we're emitting at the peak radiation is emitted at longer wavelengths. And if we have a warmer temperature, we have a peak at shorter wavelengths. Okay. So these 3 temperatures are typical temperatures. You remember that from the first plot on the temperature structure. This is a temperature that's typical at the surface in the tropics. Okay. And then this is a temperature that's typical for the tropopause high in the atmosphere. So these are typical example temperatures at different locations within the Earth's atmosphere. What about another characteristic of this black body emitted radiation? Okay. So we have an object with a stable equilibrium temperature of 300 Kelvin. Now the amount of radiation that's emitted, how can we have a measure of that? Well, we can integrate the area underneath the curve, yes? Okay. So what's happening to the area under the curve as we go to basically warmer temperatures? It's increasing, yeah? And you can see that it's increasing very rapidly. Okay. So we can see that the total radiation emitted by a black body is far greater for the warmer temperature than it is for the cooler temperature. Okay. So the total radiation is basically increasing, and the frequency of the peak radiation is also changing. So we're essentially going to shorter wavelengths and greater frequencies as the temperature increases. So they're the 2 key relationships you have to remember about black body emission. Okay. Warmer temperatures mean more radiation emitted, and also the wavelength is getting shorter. Okay.
Yes. Why increase of radiation is fast, but the decrease is slow?
You mean the asymmetry of this curve?
The radiation increase fastly, but decrease slow.
Well, the actual, I mean, the Planck function, you can see that it derives from this exponential part of the relationship here. So it's kind of a fundamental, should we say, part of this Planck black body curve. Okay. So, I mean, how this was actually derived originally, actually, it's a question I don't know. The actual origins of how this was discovered, whether it was empirically or derived. That's a good question, actually. I should try and look up. But the actual shape of that curve is directly from this relationship here. So you have the for example, for the wavelength, you've got a lambda 5, but a lambda also appears in its exponential. So this gives you that shape of the faster increase and then the slower decay. So the relationship that describes how that peak changes is known as Wien's displacement law, okay, which just shows you how the peak lambda wavelength of the emission is an inverse function of the temperature. Okay. So if we integrate that equation, L, across all of the wavelengths, then we get the total emitted energy per unit solid angle, okay? And I'm not going to go into the mathematics, but essentially if you integrate L lambda over all of the basically wavelengths, you find that the total emitted radiation, okay, so that's essentially integrating across this function, is sensitive to the fourth power of temperature. Okay. So it's a highly nonlinear function of temperature. And we can see that, because you can see that if we go from 250 to 300, that the increase in the emission is much bigger than the going from basically 200 to 250. And so that shows us that strong nonlinear relationship for the temperature. And again, I haven't gone into the mathematics of the solid angle here. Normally in the 4 ESP course, I go through the mathematics of the solid angle. But if you integrate this equation over all of the angles over the hemisphere, that basically removes that pi, okay? And so integrated over the whole hemisphere, we actually lose that pi, and we find that the radiant emittance, which is independent of the solid angle, is essentially equal to sigma t to the 4th, which you recognize as being the Stephens-Boltzmann's law. Okay. So the radiant emittance, so it's the energy integrated over a hemisphere, okay, emitted from a black body at a temperature T across all wavelengths, okay, is simply related to the 4th power of its temperature. Okay. And that's Stefan-Boltzmann's. So now, knowing that and approximating the Sun and the Earth to be black bodies, we can make a simple energy balance model of the Sun-Earth system. Okay. So let's assume for the moment, we're actually going to do an inverse calculation, first of all. Let's assume for the moment, to a good approximation, that the Sun can be considered to be a black body. So this means that its emittance across all wavelengths, okay, is sigma T Sun to the 4th. So T Sun is the temperature, surface temperature of the Sun. Okay. And this is emitted over the surface area, because remember the emittance is per unit area of a solid surface, so per meter squared. And we have a Sun with a radius of Rs, and so the surface area of the Sun is 4 pi Rs squared. Okay, so the total energy emitted by the Sun is 4 pi Rs squared sigma T Sun to the 4th. Yes? Now that energy is spread as it leaves the Sun over a sphere that's as further away we move away from the Sun, then that energy is spread over a sphere of increasing surface area. Yeah? So if we're very close to the Sun, if the Sun is here, then the energy emitted by the Sun is spread over a smaller sphere, and the further we're away from the Sun, the larger that sphere is. So the intensity of the radiation is decreasing, because again, if we have a certain solid angle here, if we move out you can see that that solid angle will be much larger further away from the sun. So the radiative intensity is decreasing. Okay. So you can see here in this cartoon, it's just explaining this. It's the inverse square law. If at a distance of 1, the radiation here that's measured over this 1 square block, if we move a distance of 2 units away from the sun, this same area here corresponds to an area of 2 by 2 of these blocks. Okay. So the radiative flux here is distributed over a wider area. So if we integrate the radiation in this square of the same size as this one, we'll have 4 times less radiative energy passing through that square. Okay. And likewise here at 3 distance, then we have a 3 by 3. So now the radiative intensity is 9 times lower. So that's the inverse square law. So at a distance of RD, we're essentially spreading the energy over a surface of a sphere of 4 pi RD squared. Okay. So we had sigma t to the 4, and then we had 4 pi rs squared was the emitted radiation. That's then spread over a sphere of 4 pi rd squared. So the 4 pi's cancel, and we find that the irradiance, E, in watts per meter squared, at a distance rd from the sun, is sigma t to the 4 rs divided by rd squared. Okay. Is that clear? So we have the sun and the Earth system. We have a distance rd. Okay. We have essentially here sigma t sun to the 4th. Okay. Spread over 4 pi rs squared. But at a distance of rd, that's divided over a sphere. So we have 4 pi id squared, and that's why we have this relation of rs divided by rd squared. So if we were to measure at the outside of the atmosphere of the Earth, we have a satellite and we're looking towards the sun, and we're measuring from a satellite in space the solar radiation. This is known as the solar constant, S0. Okay. So this irradiance is known as the solar constant. So measurements from satellites show the solar constant to be on the order of 1,370 watts per meter squared. Okay. Which varies more or less by about a meter per square over the solar cycle. Okay. So what we can do, in fact, is we can actually invert our energy balance model now. If we know what E is measured from the Earth, we can actually calculate, if we know what the distance and the radius of the sun is, we can calculate what the temperature of the emitting body is. So if we do that, we rearrange that. T sun is Rd by S squared, S0 divided by sigma, the Stefan-Boltzmann constant, remember, 5.67 times 10 to the minus 8. And then we take the 4th root. That gives us an approximate temperature of the sun of 5,800 Kelvin. Okay? So pretty warm. So why is this going to be important? Well, straight away we can see that that's a lot warmer than the Earth's temperature. So already you should start to think to yourself, oh, hang on a second, that's going to change drastically the peak of the radiation that's emitted, and also the amount. Remember that curve? The curve before wasn't changing very much because we were looking at temperatures at different points in the Earth's atmosphere. And so we were going from 200 to 300 Kelvin. But 5,800 Kelvin is a big difference. Remember, we have like the lambda. It was a very strong nonlinear function of temperature. Okay. So, but we'll come to that in a moment. So what about the... So the solar cycle is just, if you remember, the sun is a very, that picture showed it to be a very turbulent ball. It's not like a static rock object. So you have these very turbulent convection motion on the surface of the sun. So you have thermals. It's a little bit like the same motions we have for thunderstorms that make rain here. So you actually have circulations on the surface. We have them on the Earth as well. I'm not a solid Earth geophysicist, but within the molten part of the Earth, we also have circulations of the warm liquid rising and the cold liquid falling. And those motions basically move the solid plates on the Earth's surface. So that's why all these earthquakes now are the result of convection that's going on inside the Earth. You see, the convection is moving the liquid, and it's moving the plates on the surface that over, basically millions of years moves all the continents around, and those continents slide over each other, and when they slip suddenly, that's causing the earthquakes. Well, the sun doesn't have a solid crust. It's much hotter. So then you have these thermal overturning, and that overturning and the changes has a long periodicity that changes by a very small fraction the outgoing energy that's emitted. So it depends on the activity of this overturning. Certainly not my area of expertise, but in a kind of brief description, that causes a long-term variation of around 1 watt per meter squared in the outgoing energy that's emitted from the Earth. Does anyone mind if I open this window? I'm absolutely baking in here. Are you all too hot? There's no... I'm warming up as the lecture goes on. So what this cartoon here is trying to say is what we want to look at now is what is the... We know now if we just have a satellite sitting in a geostationary orbit above the Earth, how much radiation is arriving at the, should we say, the boundary of the Earth atmosphere system. So that was 1,370 watts per meter squared. So if we had basically a square plate of 1 meter squared, and it's just sitting outside of the Earth's orbit, always pointing towards the sun, it's measuring 1,370 watts per meter squared. Okay. Now what I want to calculate now is on the Earth, what is the average energy that's absorbed by 1 meter squared of the Earth's surface? Okay, and the Earth is rotating, and it's a sphere. We can treat it as a sphere with a radius RE. So we have this Earth that's rotating, and it has a surface area, you can tell me, of 4 pi RE squared, yes? Okay. Whereas the energy that the Earth is intercepting, remember, 1 meter squared basically intercepts 1,370 watts per meter squared, yes? But the total energy absorbed is not just 1 meter squared, of course. It's actually the area of a perfect disk. So if we can imagine, we slice the Earth through the middle, it's saying, what part of the sky, if you're standing on the sun and you're looking out, what's the area of the sky that's occupied by the Earth? So you can have a disk here, which has an area of pi RE squared, yes? So that area is the amount of radiation that's absorbed. So it's 1,370 multiplied by pi RE squared, that disk, okay? So that's the total energy that's intercepted by the Earth. And that energy is distributed over the Earth's surface, yes? So we have S0 pi RE squared. That's the energy that's intercepted by this disk. And that's distributed over the surface of the Earth, which is 4 pi RE squared. Okay? So that tells us that each, of course, the pi cancels and the RE squared cancels. So we just simply have S0 divided by 4. So what that tells us is that if we have a 1 meter squared disk just sitting at the distance outside the Earth on a satellite, it measures an incoming radiation of 1,370 watts per meter squared. But an average 1 meter squared on the Earth's surface is having 4 times less radiation, so around 340 watts per meter squared. So this, of course, is not true for every square meter. Some will receive more and some will receive less. It depends where you are on the Earth's surface, of course. But the average is 340 watts per meter squared. Okay.
So this S0 over 4 is a rough approximation, right?
But it's, I mean, this is extremely accurate to the assumption, the fact that we're assuming that the Earth is an exact sphere, which is a very good approximation.
Yeah, but I mean, this okay, we have some angles, right? I mean, okay, if we consider these lines that comes, the radiation line that comes from the sun, and then the heat at the ground, then there is, I mean, when we calculate the flux, we include the angle that makes.
Okay, so what this is saying is per watt is the amount of energy absorbed by a 1 square meter plate that's basically parallel to the surface of the Earth. Now, if you had like a mountain that's on an angle, okay, then of course per square meter you actually have less radiation, but then you have a larger surface area. So essentially you would have to just, for example, multiply it by the cosine of the angle. Is that right? Cosine? Yeah, cosine. If you measure the angle from the parallel to the surface of the angle.
And here the surface of the Earth is somewhat uncurved, so.
Yes, but the principle remains the same. Per square meter of parallel area, this is an exact calculation. So it's a different matter if you increase the surface area by undulating. But per square meter of parallel area, you have exactly 340 watts per meter squared. Okay. So, and the danger of overrunning, I will just finish off the next 2 slides, just so we're at a nice point to make a break. So I already mentioned planetary albedo. So as we've already said in the introduction, not all of the radiation that's arriving at the Earth just makes it through and is absorbed by the Earth, in fact. Some of the radiation is actually reflected back out to space by snow and clouds and so on. And so this ratio of the reflected solar radiation to the incident solar radiation is known as alpha P, is the symbol we use. And that's the symbol that we use for the albedo. So it's saying how much of that radiation is reflected back to space. And a good rough value, in fact, for the albedo is around 0.3. So around 30% of the radiation is reflected back to space. So the actual amount that's absorbed is S0 over 4, 1 minus the albedo, because we lose reflected back to space 30%. And so we have about 240 watts per meter squared that on average is absorbed at the Earth's, by the Earth atmosphere system. Okay. So I think actually that's a good place to break. And what we're going to do at the beginning of the next lecture is start to put together the emission part from the Earth's surface. And then what we're going to see is how important it is, the fact that the temperature of the sun and the Earth are very different. So what we're going to see is that the radiation that's emitted by the Earth's surface and the sun are almost completely non-overlapping in 2 different parts of the, should we say, electromagnetic spectrum. Completely different sets of wavelengths. And that's going to be important because we'll see that some gases, okay, CO2 for example, are transparent to radiation in some wavelengths. So the wavelengths that arrive from the sun at the short wavelengths, okay, high frequencies. So the short wavelengths, large high frequencies, will pass through and not be interacting by CO2. There won't be any interaction of the atmosphere with those wavelengths, but they are radiatively active and interact with the radiation that's emitted from the surface of the Earth because it's in a different set of wavelengths. And that's why it's really important from the lecture. The message from the radiation part of the lecture you need to take home is you need to remember that the wavelength of the radiation of a black body is highly sensitive to temperature, T to the 4th. Remember that we had for the total radiation integrated across wavelengths. But remember the Planck function, was essentially a strong function of the temperature and the wavelength, and that the peak radiation changed with the temperature of the body. And that's fundamentally important for the next lecture that we're going to have. Okay, I'll finish there. Thanks for your attention.